Hey Math 30, welcome back. In this video, we're going to be talking about optimization, one of the most important applications of first semester calculus, one of the most important applications of the basic derivative that we've learned so far, and all the derivative rules we've learned so far. And the issue we often want to solve in real life is, how do we maximize or minimize something? How do we maximize profit or minimize costs or maximize the minimize the length of time it takes to drive from point A to point B, or to maximize our fuel efficiency in our car? These are all you're doing maximum and minimum problems intuitively all the time in your life, trying to maximize your earning potential, trying to maximize how far your money goes when you're buying things and minimize your costs. You're doing this all the time. Calculus gives us the tools to study those things analytically using functions. Okay, so brief overview. We're going to talk about what does it mean to optimize. And really, that's a focus of this whole section, so that'll be implicitly in everything. We're going to have some general guidelines we're going to go through. We're going to have some general guidelines, and all of these problems are applied problems. Well, a couple are kind of abstract, but most of them are real world applied. The first key is to read the problem and understand the situation, understand the language. You often need to draw a picture, not always, but most of the time. You'll need to create some variables for the unknown quantities and fill in constants for the known constants that are given. You need to write down some kind of equations or relationships that relate the variables. Sometimes you need more than one equation. But we ultimately need to combine them into one function where the value we want to maximize is isolated and it's written equal to all the other stuff. And then we take the derivative of that and use the first derivative test or other test to find the max and min. Okay, so let's just jump straight into some discussion about it. So what does it mean to optimize? When we want to optimize something, making something optimal, it usually means we want to maximize or minimize something. So in context here, it could be what production level would minimize our cost per unit. That might be a business application. What angle should we fire a projectile to maximize the horizontal distance traveled? If you were to shoot something at 90 degrees straight up, it doesn't travel very far because it actually will theoretically land right where it started, so the distance would be 0. If you shoot something straight horizontal, it actually just falls to the ground. So there's an angle there where you can maximize how far something travels. Let's see, what dimensions should our can be to minimize the cost of production? Okay, so soda companies have already solved these problems, and they've created cans that minimize the cost. What should the dimensions of the fence be to minimize cost of production? If you fence in an area with sort of a inefficient length of fence, it could be really expensive. When the Earth is closest to the sun during its elliptical orbit. What I'm saying here is we want to minimize. Sorry, I kind of misworded that. We want to minimize when the Earth is. Sorry. Now I realize the way I worded this. Sometimes you might have a question like, when is the Earth closest to the sun during its elliptical orbit? So that's actually interesting. The Earth's orbit is not actually circular. It's slightly elliptical. And so there are times where the Earth is slightly closer to the sun than others. And this is ultimately a minimization problem because we would be minimizing the distance to the sun. And we would be minimizing where that ellipse gets closest to the sun. So basically, whenever we're trying to optimize something, we're looking for a min-max. Honestly, the calculus is usually the easiest part of this. The hardest part is usually understanding the question and setting it up. And occasionally, the algebra can be a little tricky, but usually the calculus is not the hardest part. Your book has a really nice outline, which I invite you to read. Go look for this in 4.7. And it basically, if I'm going to summarize it in a second, but basically it says understand the problem. They give you some ideas. So first step, read the problem carefully. Ask some questions about the unknowns, what's given. Key one, draw a diagram. In most problems, that's true. It's useful to draw a diagram. Introduce notation. So in their notation here, Q is their quantity that they want to maximize or minimize. So ultimately, you want to create symbols and variables for all the different quantities that are in the problem, maybe X, Y, some constants like A, B, C, or some parameters. And it's nice to make the variables kind of match what it means. So A for area, H for height, T for time. That kind of helps you keep track of things. Also easier for a person to read it. Then express Q. Express Q in terms of the other variables in step 3. Sorry, I'm trying not to select that, but now if you've written Q equals stuff, if it's written in more than one variable, sometimes you have to substitute things because you ultimately want Q to be equal to a function of a single variable. Because this course only has single variable calculus. We only know how to do derivatives when there's a single input variable. So we ultimately want to get an equation Q equals f of x, where x might mean something in that problem. Then you just use the methods that we've done in the previous sections, max, min, the absolute, the extreme value theorem. I've kind of summarized this into this. Understand the problem, draw a diagram, introduce notation, identify the quantity Q that you want to max or minimize, create variables for the unknowns, constants can be substituted, express Q as a function of the other variables, and then get Q equals the stuff. And you want the stuff to be a single variable. Then use the method from prior sections to maximize or minimize that function. Okay, let's start looking at some examples, and I'll keep these notes over here on the right. And let's just look at this one. Don't know why I have that scooted way down here. I guess it doesn't really matter. Find two numbers whose difference is 100 and whose product is a minimum. So notice this one's just purely abstract numerical, so we don't need to draw a picture. But I noticed that we are being told we have two numbers. Do we know those two numbers? No, we don't. We need to find those two numbers. So let's give them variables. How about just x and y? Their difference is 100. So if their difference is 100, that means x minus y equals 100. And their product is a minimum. So that means xy equals what? Well, we don't know what xy equals. Let's call that P for product. Notice the language here. Product is minimum. So that means we want to minimize the product, and we're going to label that P. One of the most important parts of these is read the question and figure out what you want to maximize or minimize. Because since we want to minimize P, then I know we need an equation. Equation/function. We need an equation which is a function. Like this. P equals stuff. And the stuff needs to depend only on one variable. Well, I've already almost got that. I've got P equals stuff right here. The only problem is we don't know how to do the derivative of P equals x times y very easily with two variables. We could do implicit differentiation. But the better way to do this is to just use these two equations and substitute. So let's switch to black, and now we're going to do our final work. So let's bring these down here, and I'm going to rewrite them as x minus 100 equals y. and x and p equals x times y. Now, all I did was I just subtracted the 100 over and added the y over to the right. And now we can actually just do a substitution, because what we want is we want p of x equals equals stuff with only x. And I'll do that by substitution. Okay, so back to black. P equals x, but instead of y, I'm going to put x minus 100. Okay, honestly, the hardest part of the problem is done. Understanding like what's going on and kind of like working out some equations. If you're ever stuck in this part, just start writing down equations that you think are true based on what they discuss up here. So I wrote down the difference. I wrote down a product. I identified what I wanted to maximize or minimize. That's the product P. And then I started thinking about, well, I need to take a derivative, so I really need P prime. And I want P prime to only depend on one variable, so we can use our single variable calculus. So what I'm going to get is P equals x squared minus 100x. I just need to minimize this function. Figure out what it is. So let's find P prime. 2x minus 100. A minimum, excuse me, I forgot. Yeah, we're minimizing the product. A minimum of this is going to be at a critical value. Oh, by the way, just a little comment. Do you notice that this has got to be a parabola that goes this way because the leading coefficient is positive? That's good, because our minimum is going to be wherever that parabola has a vertex. So that's kind of a little check, like, does this function even make sense for the situation? Absolutely it does. Wherever that product is at its minimum, that x value is going to be our answer. Okay, so we set this equal to 0, 2x minus 100. Add the 50 to the other side, divide by 2, you're going to get x equals 25. So we have found our x value. Let's go back and make sure that, what do we need to find? It says find the two numbers. So we need to find x and y. But all we need to do is plug our x back into our relationship between x and y, and then we're done. So what I can do is come down here and use that green equation in the top left and just get this. So that means 25 minus y equals 100. And so we get that we get that y equals, so if I add the y over to the other side, subtract 100, I get that y equals negative 75. Okay, so let's also double check. Is the difference between these two numbers 100? It is. The difference between negative 75 and 25 is 100. Negative 75 plus 100 is 25. So that works. And their product is minimized. We could actually go graph our product function. This is one way you can kind of check yourself if it makes sense. I can go P equals x squared minus 100x. So I just graphed, what I did is, and I'll switch and show you in just a second. I just graphed this. And let's show that. Now this is a super stretched out graph because this 100 is a pretty large number. So I can like zoom out, and then it looks like I'm going to need to change the scale. So let's do this. Now remember, this horizontal axis represents our x value. And where is that located? It's located at 50. And so that, Good thing I checked my answer. I did some arithmetic incorrect. So I just realized that I double divided in my head. That's what I get for skipping steps. And add 100 to both sides, and I get 100 equals 2x, x equals 50. And then I just need to fix it. I'll come over here and put this needed to be a 50. And therefore, y equals negative 50. Okay. So I made a little arithmetic error. That's okay. By the way, I've learned that there are a lot of math teachers out there. Not throwing shade on any math teachers, but I've learned there's a lot of math teachers out there who are like worried about making mistakes. If I make mistakes that are super confusing, I try to correct that. But I make arithmetic mistakes too. I make little algebra mistakes too, and so do most people, even people who are really proficient in mathematics. And so, yeah, anyway, so what I try to show you is, hey, number one, I make errors. That was not intentional. I made an accidental error there. But I'm saying, hey, use technology to check your answers. Figure out ways to try and check your work and by the way, the more you do that, the more you'll actually learn the math, because what I just did was I connected to the graph and I went, actually, yeah, so that does make sense. It needs to be 50. And so here's our answer. We've got our answer. Cool. They differ by 100, and it minimizes the product. By the way, the product of those two would be negative 2,500, although they didn't ask for that in the question. But there it is. Yeah, I'm not afraid to show that I mess up. It's all good. Let's see. So find two numbers whose difference is 100 and whose product is a minimum. Uh-oh, did I copy the same? Oops, I accidentally copied the same question again. Okay, so skip that page. Okay, what is the minimum vertical distance between the parabolas y equals x squared plus 1 and y equals x minus x squared? Okay, so we've got two parabolas and we want to minimize the distance between them. So I can see that we've got, we need to figure out a way to represent d for distance. Because I see in the question we want to basically minimize distance, whatever that means. But it says we want, I'm paraphrasing, we want to minimize distance. Okay, so we want to minimize the distance. What can really help with problems like this, and let me actually slide this up so we have a little room. Okay, that should be good. What can help with a problem like this is to graph the situation. So even if you were doing this by hand, you could think about, okay, what do these two graphs look like? Well, I know that the first one is a parabola with a y-intercept of 1. So I know the first one looks like this. Maybe I should have made this a little bigger, but oh well. I know, so this is, that one's in blue. Let's do this one in green. Y equals x minus x squared, which is x 1 minus x. So it has x-intercepts at 0 and 1. And I also know that it is shaped like this because the coefficient in front of x squared is negative. That's kind of confusing the way I did that. I know it's shaped like that. And you could figure out the vertex or whatever, but I can just tell you that the vertex is always halfway in between the x-intercepts, and it's gonna be something kind of like this. Now, if I were to pick any one point on this graph. Let me actually take this. I think this should work. Let me make this a little bit bigger so that I can zoom in a bit more. And I know I didn't draw this like the best in the history of graph drawing, but I think it should be clear enough, I hope. The distance between these graphs is this vertical height. So this would be D. But can you see that there are different places where the distance is much greater and the distance is much less? So there's going to be a place where the distance between the two is minimized. Okay, so we need an expression for distance. D is equal to the blue function value minus the green function value, because the green one's below. You could do absolute value and then do it either way. But in this case, since we're finding the difference, we want the one that's greater above and subtract the one that's below. So the picture really helped here. So this would be x squared plus 1 minus x squared. Now, what I have here is, let me just show you the graph of the situation. I do have the graph of the situation. Colors are different than what I drew, but it's okay. Actually, I can even change that so that they match. I got the blue one on top and I got the green one on the bottom. Okay, cool. Now, what is D? D is gonna be this. It's gonna be y equals excuse me, it's gonna be a vertical line. X equals A. Let me quickly make a, let me just do a little cheat here. Okay, so I have A as a parameter that I can slide. And x equals A is gonna be vertical, but I wanna limit that to be, I want my y values to go at the least, they're gonna be at g of A, less than or equal to y, less than or equal to f of A. So I'm just doing this so that you can see the graph. So what I've just done is I've just graphed a vertical line that represents the distance. So the length of this black line is the distance between the two. This function, not a function, but this vertical line has y values that are, the minimum is at the green graph and the maximum is at the blue graph. And now if I slide this, do you notice that this changes? The length of this changes. Let's see, somewhere in here, the distance appears to be minimized. So I think my answer needs to be somewhere around, I don't know, somewhere around 1. Do you notice that at x equals 1? Oh, I'm sorry, this is actually a equals 0.2. I was misreading the graph. That's not 1, this is 1. So somewhere around 0.2, looks like the distance between the two is minimized. Okay, so back to the handwork. So that's kind of like just a way of looking at the problem. And I will include a link in the notes to what I just did so that you can look at it once I post the notes. Okay, so we've got our distance function, which is the top graph minus the bottom graph. And what we need to do is we need to minimize D. So we need to minimize D. Let's do it. Okay, we're doing our final work, so I'll switch to black. All of our thoughts are in different colors. So I have x squared plus 1 minus x plus x squared. So I'm just simplifying this D function. 2x squared minus x plus 1. Okay, so we have that. We could check that graphically, but I'll just do it this way. So we've combined terms here. 2 minus negative x squared is 2x squared. I've got negative x, and I have plus 1. 4x minus 1 is the derivative. Oh, this is looking good. This is going to be close. Here's why I'm saying that. And I'll go slow on this so I don't make the same mistake I made on the last problem. So we want to find the critical values. Critical. And the critical values is when d prime equals 0. And we get 1 equals 4x, and we get x equals 1/4. Remember, we were estimating that the answer might be somewhere around 0.2. Well, 1/4 is 0.25, so this is looking pretty good. So this means that x says, what is the minimum vertical distance? So we actually need to answer what the minimum distance is between the two. What we have found is the x value that minimizes distance. So this is the x value that minimizes distance. So all we need to do is plug that back into the distance function. So we get d of 1/4 equals 1/4 squared two times 1/4 squared minus 1/4 plus 1 equals 2/16 minus, well, 1/4 is 4/16 plus 16/16. I'm just getting a common denominator. 16 minus 4 is 12 plus 2 is 14. 14/16. 7/8. Let's go check. Okay, let's go back to here. And let's actually make a function. D of x is equal to the blue graph minus the green graph. So now d of x represents the distance between the two. And where is it minimized? It's minimized at, see the purple graph represents the function that quantifies the distance between the two. It is minimized at 0.25. And the output is 0.875. What is, we found that the minimum value was 7/8, so let's calculate 7/8. And so our answer was 7/8, which is 0.875. And the minimum value, the minimum distance on the distance graph is 0.875. So we have just checked graphically that we have found the correct minimum. Cool. I'm going to make sure to copy that. I just don't want to forget to put it in the notes so that you have that graph to look at. And I will put it over here. Let's paste that. Yeah. Control Z. Okay, good. So I have it in the notes. It'll be over on the side. And I'll call it link to graph. Cool. All right. And let's do one more here. And I'm gonna have to split this up into multiple videos, and mostly because I want to take time to go through some key examples that are on your so by the way, I got the link to the graph there in the notes. I want to be able to go through some examples that give you really classic problems that are very likely to be ones that could be on the final, I guess I should say. I mean, there's going to be one or two kind of optimization problems on the final, at least one for sure. Okay, so find the dimensions of a rectangle with perimeter 100 meters whose area is as large as possible. So we want to find the dimensions of a rectangle. I'm just going to draw a rectangle. I'm going to draw a picture. Perimeter 100 whose area. So they mentioned perimeter and they mentioned area. Well, we definitely need an equation for area and we need an equation for perimeter because they gave us that P is 100, but we also need an equation for perimeter. I clearly need to give my sides variables, and it's a rectangle, so we don't know if the sides are the same or not. Remember, a square is a special case of a rectangle, but I'll label it that way. So the area is x times y, and the perimeter is 2x plus 2y. Cool. What do we want to maximize or minimize? Oh, we want to find the area that is as large as possible. So we want to maximize area. I think I won't actually solve this all the way out. I'm just going to help you set it up. I'll show you some setups for a few problems. We want to maximize area. Okay, so that means we want to maximize this one. But we definitely want, I would like to be able to substitute away y. So I think what I'm going to do is over on the side here, I'm going to solve for y on this equation. Little side work. P minus 2x equals 2y. Divide both sides by 2, I get y equals p minus 2x over 2. And so I can substitute that into here. A equals x. P. Oh yeah, and so I just want to also be clear that. I could even actually fix this. Remember that they gave us that the perimeter is known? I could have actually plugged in 100 from the very beginning. I wrote P here, but I actually realized that that's a constant. So I could put 100 there. And I can put... Why isn't that erasing? Okay, there we go. And so this is actually 100. And this is 100. So this is y is 100 minus 2x all over 2. And I'm going to leave it there. You would just need to maximize A. You would just need to maximize A. So find A prime, set it equal to 0, solve for the zeros, and check that it's a maximum. We want to make it. And actually, I have the answer here for you. So you could actually, the answer is that the maximum area is when it's actually a square. So when x and y are equal, and they're both 25, that will be the answer. Okay, so you can actually try this one. The setup is actually the most interesting part, the hardest part that I'll help you with. Here's another example. A model used for the yield y of an agricultural crop is a function of the nitrogen level N in the soil measured in appropriate units is y equals Kn over 1 plus n squared, where n is a positive constant. What nitrogen level gives the best yield? Okay, yield is a word used in production to be like the largest amount produced. It's used specifically in production of agriculture. So what we have here is a function where k is constant. They didn't give us k, so I'm assuming it doesn't matter what k is. Y is a variable. N is variable. N represents the level of nitrogen. Y represents how much crop is grown. They've actually already given us the relationship we need. So this is one where you don't need to build the equation that you're going to maximize. We actually, let's be clear. It says what nitrogen level gives the best yield. So that means we want to maximize Y. So all we need to do is find Y prime. So if we have Y equals Kn, and we need to keep in our mind that N, Y is really an equation with, I'm going to say Y of N, because the input is N and the output is Y. Okay, so let's, so we want to maximize Y, and they gave us the equation, so this one's nice. And you might get a problem like this on the homework and on the exam as well, where you're actually just given the relationship and they say maximize the output or minimize the output. Find the level of N that makes Y maximum. So we just need a derivative. We got to keep in our mind that N is a variable and K is a constant. We just don't know what K is. This is definitely quotient rule. So this would be the bottom. I am going to do this one. So bottom times the derivative of the top, which is K, minus the top times the derivative of the bottom, divided by the bottom squared. Okay. Well, we need the critical values of this. There's no place where this is undefined. The denominator will never be 0. And even if it was, that same value would not be in the domain of the original function, so we wouldn't even worry about it. So all we need to do is set this equal to 0 and solve. 0 equals, by the way, before I do that, I could simplify this slightly. So this is K plus Kn squared minus 2Kn squared. Which equals K minus Kn squared. So I know this kind of trips up students sometimes, but do you notice that all the letters here are the same as the letters here? The variables and constants are the same. So I have 1 Kn squared and I have 2 Kn squareds. 1 minus 2 is -1, so I'm left with -1. So, -1 Kn squared here. So this is 1 Kn squared minus 2 Kn squared. When you combine them, you're only left with -1 Kn squared. Okay, cool. All right, so let's find our critical values. The critical values are where this is equal to 0. Okay, this fraction can only equal 0 when the numerator is 0, because the denominator can never be 0. So what that means is we can write 0 equals K minus Kn squared. Remember, K is a constant, so we have 0 equals K, and I can even factor out K. 1 minus, not X squared, N squared. That is a difference of squares, so this factors. There's a couple ways you could do this. Let's just factor it. X minus N, 1 minus N and 1 plus N. And remember, we want the N values that make this true, so what I get is N equals 1. And N equals -1. Those are the two values for N that make the derivative 0. So those are the potential critical values where we are going to minimize the yield or maximize the yield. Okay, let's think about that for a second. Okay, so we're trying to find the level of nitrogen that maximizes the yield. So does it make any sense to have a negative value of nitrogen? Not really. If we're going to measure a quantity of nitrogen, the least you can have is 0. So although we theoretically found n equals -1 as a solution, we reject that one because n needs to be positive. Okay, let's go check verbally, like what are we asking us to find? What nitrogen level gives the best yield? Now, they didn't give units. If they gave units, we would have to put the units, but the answer is n equals 1. N equals 1 gives the best yield. N equals 1 maximizes the yield. Now, how could we argue that that is a maximum? There's a couple ways. You could do a number line. Remember how we did a number line and we test the left and right of 1 and see if it makes the derivative negative and then positive, so it would be decreasing and then increasing. So you'd want to be able to go back and use those techniques that we used in previous chapters to find, like, is it a minimum? Show that it's a minimum. How do you do that? You do the first derivative test and you do the increasing decreasing test. Okay, so, but I'll just cut to it and call that the answer to this. I'm assuming you remember the previous sections. And I have a graph here that I've linked below, but I actually have the graph. Because you know what's interesting is that, do you notice that k didn't even matter? K could have been any positive constant and we would have gotten the same answer. In the end, the k didn't even matter. Since k is positive, this can only be 0 when n makes the function 0, since k can't be 0 and k is not a variable anyway. Okay, so here's the graph of the situation. And let me turn this off for a second. I'll do that. Well, let me turn, let's see. I thought I had, I'll turn these off. I'll leave that one on. Okay, so what we have here is I've actually graphed the function y of n equals kn over 1 plus n squared. And since it only makes sense for nitrogen to be positive or 0, I've limited the domain to only positive values. That's on the horizontal axis. And the k value I've actually put as a slider so we can change k. And you notice that as I increase or decrease k, that max point is always on this line, n equals 1. So regardless of this other constant k, the max value is always at n equals 1, and all this k does is change the shape of the graph, make it taller, make it less. And the maximum yield I've actually marked here is variable in this example. The maximum yield is whatever that height is, that's the yield, is whatever that height is of that maximum. But the input's always n equals 1. So the nitrogen level of 1, in this case, is what maximizes the yield. Now, Desmos forces you to, when you do the derivative f prime, it forces you to use x. So I've also graphed the function f of x, but I didn't graph it. It's actually the same graph. So it's just the same graph, but f of x is this blue graph. So f prime of x is this blue graph. So that's the derivative we found. And notice where the derivative equals 0 is the place where the yield is maximized. And I've got some labels here. So this is, I've got some labels here. So this is y prime. And where, notice that even when we change k, do you notice that the derivative always goes through the x-axis at n equals 1? Even as we change k, the function changes, the derivative changes, but the critical value doesn't change. And the value that maximizes the yield doesn't change. but the maximum yield changes. Okay, so there's a link to this graph in the notes already. Okay, so that's the last one I'm going to do on this video. I've helped you kind of like set up some, and by the way, you're going to see a few problems that are almost identical to the examples I had in this. I'm going to follow up with video with just a few more examples where I help you do some setup. I'm going to give you some homework hints directly where I help you set up ones that are in the homework. A couple of them are a little tricky. Setup is often the hardest part. I'll give you some hints and help because they're classic problems that if you understand those examples, it'll be much easier to understand ones that are kind of have a similar makeup, which could be on the final. And there was one about the cost of a can in a previous final exam. So those will also be available for you to study. So, all right, I'll see you in the next video.